This single topic video will cover topic 4.6, watersheds. Water on Earth exists in many forms. It can be frozen, as in snow and glaciers, liquid in lakes, rivers, seas, and oceans, and gas as water vapor in the atmosphere. Some water is fresh water, and some is salty. Water even exists underground. As precipitation, water falls to the ground sometimes in liquid form as rain, and if conditions are right, other times as a solid, such as snow or hail. Falling on land, some water accumulates on the surface, while the rest infiltrates the soil and percolates underground. By definition, a watershed is an area of land into which water that falls ends up draining into a common location. That could mean, as it travels downhill, it ends up in a pond or lake. Perhaps the ultimate destination is the ocean, or it might end up stored underground. Characteristics of a watershed, like its geologic features, flora present, and soil permeability and porosity, all contribute to how water travels through it. On a planetary scale, we can observe a number of watersheds and their drainage areas. This map illustrates the concept. For example, were a drop of precipitation to land in the area color-coded pink, be it in Western Australia, anywhere in India, the eastern tip of Somalia, or the island of Madagascar, that water will eventually make its way to the Indian Ocean. Of course, the force responsible for water's movement on the ground or under it is gravity. Where precisely it lands, however, could mean that the journey to the ocean might only take days or weeks, perhaps even centuries or millennia. Although most of the watersheds on Earth eventually lead to the oceans, there are some that are contained exclusively on land. These endorheic watersheds are contained on land due to geologic features and underground rock formations that act as barriers, trapping water within them. Here in North America, there are 7 major watersheds. Just as with the global examples, water falling into any one of these areas will find its way into a particular destination. Precipitation in the Canadian province of Manitoba flows into Hudson Bay. Anywhere in the state of Washington, however, means that the Pacific Ocean is where the water will eventually end up. For most of the United States, the Mississippi River Basin, along with all of its feeder rivers and tributaries, is of significant importance, especially to agriculture. North America's only endorheic watershed, the Great Basin, includes nearly all of Nevada, with portions of Oregon, Idaho, Utah, California, and even a sliver of the northernmost portion of Baja California. The lines on this map indicate continental divides. They delineate each of the watersheds, marking the dividing line as the highest point among them. Precipitation falling on one side of a continental divide goes one way, whereas that which falls on the other side goes in another direction. Closer to home, the Puget Sound region has a variety of much smaller watersheds. Each of the color-coded watersheds in the map are all west of the Cascade Mountains, draining into Puget Sound or the Strait of Juan de Fuca before ending up in the Pacific Ocean. You may recall from the previous slide that I mentioned all of Washington belonging to the same watershed. While that is true, precipitation on the east side of the Cascades makes its way to the Pacific Ocean via the Columbia River to our south. As collectors of water, how water moves through a watershed, be it on the surface or underground, is influenced by a variety of factors. Soil characteristics, including how much sand, silt, or clay is in it, determines how permeable it is to water. Soil permeability is a measure of the ease with which water can move through it. Soils rich in clay, for example, demonstrate poor permeability, while those high in sand content are the opposite. When soil is already saturated with water, more water is very unlikely to infiltrate the surface and get underground. Probably as no surprise, steeper land allows water to move downhill more quickly. This faster surface flow results in streams and rivers with straighter courses and much fewer twists and turns. It also means that less water infiltrates the surface since it's moving far too quickly for much of it to soak into the ground. The roots of plants help to break up soil, making it more accepting of water infiltration and percolation. And then, of course, there's our influence. There are a number of ways in which we alter the movement of water through a watershed. Removing trees and other plants obviously means fewer plant roots. Constructing dams, whether it's for water storage as a reservoir, to generate electricity, or both, results in changes to water flow. We actively drain some wetland areas to clear way for development like buildings and roads. Roads and other paved surfaces like parking lots, sidewalks, and highways create less permeable surfaces, making it more difficult for water to soak underground. Underground stores of water are called aquifers. Freshwater aquifers are important sources of water for industrial use, drinking, and, of course, agriculture. It is important to take a moment to define what an aquifer is and what it is not. An aquifer is not an underground open space or cavity like a cave that's filled up with water. What an aquifer really is underground soil and rock that is saturated with water. Some rock types are more porous than others and therefore have a higher capacity for water storage. Water moves through aquifers downhill through permeable layers. As an analogy, think of a kitchen sponge. It has many tiny spaces in which water can be held. The largest aquifer in North America, the Ogallala, sits under portions of 8 states, covering 450,000 square kilometers. It provides water for use in agriculture and drinking water for nearly 2.5 million people. However, the rate at which the aquifer recharges or refills is less than that of its discharge. Water is being pumped out of it faster than nature can recharge it. This map helps to illustrate regions where water level has declined, in shades of yellow and red, in the period shown. Areas where it has increased are shown in shades of blue. Aquifer storage decline has accelerated since the data shown in the map. In 2008, a Canadian company proposed construction of a 2,600 kilometer long pipeline to carry Canadian oil sands from Alberta to refineries in Texas. The proposed route of the Keystone XL pipeline crossed through central Nebraska, directly over the Ogallala Aquifer. Opponents of the route were concerned about the possibility of contamination from leaks or spills from the pipeline. Although the debate about the pipeline spanned the administrations of 3 U.S. presidents, the Canadian company dropped plans entirely for its construction in June of 2021. That's all there is about watersheds. Thanks for watching, and take care.